Welcome to Hydrates. In this experiment, you'll learn how to identify hydrates, you will study the stability of hydrates, and you will also actually determine the formula of a hydrate. Now, in general, hydrates are crystalline solids which actually contain water molecules in their lattices. Not just the elements of water, but actual water molecules. And they form stoichiometric compounds, where here X and Y are small integers. And they are very prevalent. For example, the setting of cement or concrete and the setting of plaster, these are all examples of the formation of hydrates. Now water, H2O, is a small but polar molecule. That is, it has an unsymmetrical charge distribution. The oxygen end here is partially negative and can attract cations. The hydrogen ends are partially positive and can be used in hydrogen bonding or be attractive towards anions. Now, the polarity of water accounts for its being such a very good solvent, and also then accounts for the fact that it will form hydrates. To visualize hydrates more easily, think in terms of this carton of eggs, where the eggs here are the molecules or ions in a crystal. Note they're very symmetrically arranged and very efficiently arranged, almost as efficiently as in a crystal. But here we have spaces which we are using so that the eggs don't bump up against each other. In a crystal, we can use them differently. Because water is polar, it can very efficiently occupy some of these empty spaces in the lattice that you have here originally. Now, what you end up then with it is not only a lattice of ions and molecules that you started out with, but the regular lattice then of the water molecules as well. Hydrates, therefore, have an exact formula, and they are not like solutions, water solutions for example, which can have a considerable range of concentrations. The stability of hydrates is overall most dependent on the nature of the compound itself. For example, small cations will tend to encourage the formation of hydrates. It is also dependent on temperature. Now, if you take a hydrate and heat it, it will decompose to give off water. And finally, if you let a hydrate sit out in the air, if the relative humidity is very low, like most anything else, a hydrate will tend to dehydrate. To identify a hydrate, you must heat it. If it gives off water, it may be a hydrate. If it does not give off water, then it is not a hydrate. So, if it gives off water, did it change color while giving off water? Or did it change anything while giving off water? If so, does adding water make it revert back to its original form? Now remember, Humpty Dumpty can't really be put back together again, so that you have to make some judgments here. The other thing is, look at its anhydrous formula. If the anhydrous formula does not contain H or O, it cannot decompose to give water. So therefore, if the material that you heated gave off water, and its anhydrous formula does not contain hydrogen or oxygen, then in fact it must be a hydrate. To demonstrate identifying a hydrate, we will use these two samples. Both have the anhydrous formula of CuSO4 or copper sulfate. And we will find out which, if any, of these is actually a hydrate. Heating the first tube. Now remember, when you put this in the flame, make sure that you do not put the top of the tube in the flame so that any water which wants to come off will condense in the top. And as you can see, there is essentially little or no water condensing. And then make sure also you do not point the top of this tube at anybody, because you don't want anything to spurt out. But heating this produces essentially no water. Heating the other tube seems to provide some sort of changes here. We're getting a lot of water coming off, and the color is changing here from a blue to a white. Well, this first tube, when we heated it, essentially gave off no water and stayed pretty much the same, whereas the second tube seems to have changed color. We have another sample here of the original, and you can see it changed color quite a bit and gave off lots of water. Now, since the water could not come from anything other than this being a hydrate, this must be a hydrate. To add additional evidence that it actually was a hydrate to start out with, we will put some water back into this. And as you can see, when we put the water back in, it turns from that whitish color, which is the anhydrous color, back to the blue color. Now, not all hydrates will be as dramatic as this copper sulfate demonstration, so you will have to make some decisions. We will now turn our attention to determining the formula of a hydrate. This will have the general form X anhydrous residue, Y water, where X and Y are small whole numbers. And to determine that, we will have to know the molecular weight of the anhydrous residue, but after that we will determine the percent of water in the hydrate, and then we will use that molecular weight of the anhydrous residue and the molecular weight of water to determine the molecular formula. You will use an electronic analytical balance for the quantitative measure of water in a hydrate. So to do that, again, when you use these balances, make sure the doors are closed, make sure the balance is level, and then make sure it goes to 0. Open the door, put on your tube. Use these notches for round objects, remember, so they do not roll. And then close the door, and there you got your weigh, 12.6893 grams. Add your unknown to the tube, set this again to 0, and then reweigh the tube with the unknown in it. There you have 14.1245 grams. You will now heat this in the flame, and again, make sure that you do not point this at anybody. Heat it in the flame. It's going to be heating pretty hot. As you can see, there's already water coming off now. Now, in this case, you want to get rid of that water, so you want to make sure that that water gets heated up and driven off. So when you're through, the top of this tube should be hot, so that there is no water. And keep heating, and keep heating. Again, be careful not to point it at anybody. Heat the top of the tube as well, again. So there you go. Finally, weigh the tube after heating, driving off all the water. Again, put it on the notches. Make sure that the tube is cool. It has to be at room temperature, otherwise you'll get convection currents in here, which will make the weight too light. And read 13.6739 grams. From our experimental data, we could make a calculation that the percent of water in our unknown hydrate was 31.40, and knowing that the molecular weight of the anhydrous residue is 118.2, one can also calculate that the formula of the hydrate is the anhydrous residue with 3 waters. That is, you don't know exactly what the anhydrous residue is, but you know there is one of those for every 3 waters. Remember, in this experiment, you're trying to drive off the water. So if after heating you see some condensate still in the top of the tube, reheat it so you drive all the water off. There are some terms which describe material changing with time, which are particularly applicable to hydrates. Now, stable, for example, means unchanging, and this is what one might expect of hydrates such as cement or plaster. Hydrates, which are efflorescent, lose water to the atmosphere. The change in the crystalline lattice frequently looks like a flower blooming, hence the name. Materials which are deliquescent or hygroscopic actually gain moisture from the atmosphere, and in so doing they probably turn themselves into hydrates. Now the difference between deliquescent and hygroscopic is that deliquescent gains so much water that it actually dissolves itself and turns into a liquid. Having trouble getting salt out of a shaker on a humid day? Well, listen up. Now, table salt is sodium chloride, which is quite stable, but it also contains small amount of impurities such as calcium and magnesium chloride. Here's an example of deliquescence. After about a half an hour of New Jersey summer and the Rutgers air conditioning, this is what has happened. The compound is calcium chloride, and it's sold in hardware stores. In the winter, it's used to sprinkle on ice to melt the ice, but in the summer, it is sprinkled on dirt and gravel roads to keep down the dust. And speaking of dust settling, I think you should now start having fun doing this experiment yourself. So, until next week, goodbye.